All right, so this is part three of deriving the TD character table. Classic character table, but I haven't seen anybody else anywhere on the internet deriving this character table because it's a little difficult to do um, and requires some, pretty difficult visualization or math. We got through it on Gamma 5 in part two. And what we're going to do is we're going to do some tricks and take care of the gamma 2, gamma 3, and gamma 4 using some other rules of the character table. So the rule we're going to take advantage of is the orthogonality rule. We know that for character tables that are well behaved, that is, they don't have complex numbers, that whenever you have a dimensionality of 1 here, you're going to have ones across ones or negative ones across the board. And this is a well-behaved character table, but what I mean by that is we didn't have any imaginary characters, and we could see that when we took the sum of the squares here and equaled, you remember it did very nicely equal 24, which is the total number of symmetry operations, the order of the point group. So we didn't have any violations of the character table rules that had us have to split things into components. You can see my other videos on that. So we're going to have ones and negative ones here. And so then let's think about what requirements we would need for gamma 1 to be orthogonal to gamma 2. So the dot product being equal to 0. And we know we have 20, remember this dot product is adjusted for the number of symmetry operations in each class. And we have 24 symmetry operations here. And gamma 1 is ones across the board. So if we're going to have a 0 be our final product, right, our dot product, we're going to have 12 of these 24s be allocated to positive ones and 12 of these 24s being allocated to negative ones. That's how we have to split it. And so here we can see that the only way to do that, to have 12 and 12, is to have 1, 1, negative 1, and negative 1. Because we have a 6 and a 6, this is 12, and here we have a 1 plus 8 plus 3 is 12. There's no other way to get 12 and 12. And so that's just a very quick way to get this. We could check this is indeed orthogonal, right? We'd have a 1 for gamma 1, 1 for gamma 2, and 1 for one operation in the symmetry class, plus 1 for gamma 1, 1 for gamma 2, and 8 for 8 symmetry operations in the C3, 1 and 1, and 3 for 3C2, and then 1 and negative 1 is what I'm talking about, where you need it to be balanced out. It's times 6, and 1 and negative 1 times 6, and that ends up equal 0, right? 1 plus 8 plus 3 minus 6 is equal to 0, or 12 minus 12 equals 0. So that's good. We can also check that gamma 2 dotted with gamma 5 equals 0, and it should be. In that case, we're going to have 1 times 3, right? 1 and 3, 1 and 3 times 1 for the identity operation. We have 1 and 0. I don't even have to write that one out, but I will. 1 times 0 times 8, just for clarity. And here I have 1 times a negative 1 times 3 is negative 3. Right here I have negative 1 times negative 1 times 6. And here I have 1 times negative 1 times 6. Okay. And so what does that get me? That gets 3 plus 0 minus 3 plus negative 3 gives 0. It's positive 6 and a negative 6 equals 0. So it's orthogonal. So that's a very nice way of how to do this. So we got gamma 2. Now that we have gamma 2, we're going to do another trick. We're going to multiply gamma 2 by gamma 5 to get a new character. We don't know a priori if this is going to be an irreducible representation or a reducible representation. We've done this trick before when we've tried to get some quadratic function in previous character tables that we wanted. Here we don't even know what function or if there's any simple functions that this gamma 2 transforms as, but we don't really care. We're going to try to take advantage of this and see if we can make something that's orthogonal. So if we do that, we're going to get 1 times 3 is 3, 1 times 0 is 0, 1 times negative 1 is negative 1, negative 1 times negative 1 is 1, and negative 1 times 1 is negative 1. And if you think about this, this actually makes sense because the weighting on 6 and 6 is the same. And so who cares if you have a negative 1 here or a positive 1 here, as long as it's the opposite here, right? Gamma 4 and gamma 5 are identical, except we just swap these and the weighting functions are the same. So all the orthogonality that's going to apply for gamma 5 is going to apply for gamma 4 because it has the same weighting function here of 6. So that's sort of beautiful that it works out that way. And then at this point, we only have one left to sort of puzzle out using, again, the orthogonality principle. So we're going to look at this here. We're going to try to be orthogonal with gamma 1. And so we're going to try to do, gamma 1 dotted with gamma 3 equals 0. And we have a 2 here. Our hand is forced to be a 2. So this is going to be a 2. And so how can we balance things out? Well, if we're forced to have a 2, okay, probably the fact that we have a 2 here means there's going to be a 2 or negative 2 somewhere else, right? And so what's a way that we could balance this out? Well, if we put a 2 or negative 2 somewhere else, let's see, if we put a 2 here, we're going to get 16 or negative 16. That doesn't seem right. It's too high, right? Or here we're going to get 12 or negative 12, again, too high. So what if we put a 2 or negative 2 there? Then we could try like a negative 2 there. That balance it out. So we could try something that there we get negative 2 give us a 6, and then maybe a 1 to balance out, and then a 0 and a 0. That would work with gamma 1. But then if we test it with some other functions like gamma 4, it's not going to work. We're going to get 6 here. This is 0, and then we get positive 6 here is 12, and then we got 18, and it just doesn't work. So you can work through this, and that doesn't work. So we have to, guess and check here. What if we put a positive 2 here? And then think about what could balance it out. Well, if I put a positive 2 here, then I have a 6. We're looking back at gamma 1, right? I have a 6, and then here I have a 2 and a 1. So I have an 8. Oh, I have an 8 here. Why don't I balance that out with a negative 1? That's balanced out, and maybe I could put 1s or negative 1s here to balance each other out. That would be orthogonal with gamma 1, right? But the problem is, again, here, they're not going to be orthogonal with the other ones. For example, we know the first 3 ones here are the same as these first 3 ones, so that balanced it out to get 0. But then here, we're not going to be balanced out, because here we would be balanced out. We have a negative 1 and a 1. That would be balanced out. What about for gamma 4? We get a 6, we get a 0, and we get negative 3. Negative 6, that's balanced out. But then here we would get positive 6, because this is a 1, and a positive 1, another positive 6. Not going to balance each other out. So that doesn't work. So the only way for this to work, because of that problem there, you're going to keep this here, and these are flipped, right? Gamma 5, to be orthogonal with gamma 5, you have to flip it too. So if it works one way, it has to work one way and has to work the other way while being balanced out. There's only one solution for that, okay? And that's going to be if you put zeros there, right? So if you put zeros there, then it doesn't matter if it's one way or the other. It's always just 0. It stays balanced. And you can see if you work through this for all these, this will work, okay? So that one's really tricky. Really have to just kind of guess and check for that one. That's the best way, I think, to do it. You could try to work with some quadratics here, but then you need to explicitly know how x, y, and z transforms in all the different directions. Very difficult to do that and visualize that. A lot of three-dimensional trigonometry that gets quite complex. We touched into that on part 2 of this video with x, y, and z, and it gets even more complicated. So this is a better way to do it. So we did it. We came up with the 25 characters of this 5x5 matrix, 5x5 character table, I should call it. We just have to replace these Mulliken symbols here. And the rules here are you put A's or B's if you're a character under the identity. Dimensionality is what we call it, is 1. So these are going to be A's or B's. And if we're symmetric with the principal rotation axis, which is the C3, highest order Cn, we give it an A. For antisymmetric, we give it a B. Antisymmetric just means a negative number. Symmetric means a positive number. These are positive ones here. So both of these are going to be A's. If you have a dimensionality of 2, you give it an E, and if you have a dimensionality of 3, you give it a T. It's a symbol. But we have to differentiate between these 2 A's and these 2 T's. This E is fine as is, and so we use subscripts 1 and 2. And for those, we just look at the mirror planes, okay? And so the mirror plane here, we're symmetric with the mirror plane. so we give it a 1. If we're anti-symmetric or a -1, we give it a 2. Here's the E, we don't have to differentiate, so we just leave it. -1 there, that is going to be T 1 is how people call it, and T2. And I'm staring at this trying to figure out why, and there's some arbitrariness to this all. Let's see, did I get that right? T1 was +1 and -1. Yeah. So why is that called 1 and 2 on the subscript? Are we following any rules here? We don't appear to be following any consistent rules. This is strange. I just realized this. Mulliken symbols sometimes can be pretty arbitrary. So there, you just gotta, they're arbitrary, right? They're just labels that people agreed upon. I guess we agreed upon that. Usually it's perpendicular C2s or that you use, okay? But this doesn't, these aren't technically perpendicular, so we're not using them there. But anyway, we got the characters here. These are just labels, right? So they're not that important. Fundamentally, they don't really mean anything. But yeah, that's a little surprising there, because what I'm saying is that, you know, here is +1, there's -1, we gave it a subscript 1. Here is +1, +1. I guess we followed the S4 for some reason. We're following the S4 is what we used, which no other point group that I know of. Maybe we could look at octahedral. No, it's not going to be that. It follows this way. So, yep, it's just a curiosity of the Mulliken symbols not being totally, you know, there's some ambiguity there. But key thing is that we're able to come up with these, you know, 25 characters using all these different tricks that we learned in derivations.